Now I'm going to start off with an older gas law. This is one of Dalton's gas laws, the same person who made the first atomic theory. And his gas law of partial pressure basically says that each individual gas exerts a portion of the total pressure. Right, so if I want to know the total pressure inside of a container, I can figure out what pressure each of the gases exerts on its own and then add them together. The other way of saying this is that if I know the total pressure, so if I know pressure total and I want to find out the pressure of any individual gas, I can find that by using something called mole fraction. The mole fraction is exactly what it sounds like. It's the number of moles of the thing that you're interested in divided by the number of moles of everything added together. Right, and the way that you'll see this in formula is this: you get the Greek letter chi, which is just a giant X, and I'm going to say X sub I. I is the gas of interest. Right, so again, just moles of gas divided by total number of moles. And if I want to find the pressure of a gas, so the pressure of gas I is equal to the mole fraction of I times the total pressure. Right, so this equation right here is what we'll use to figure out the pressure of any individual gas. So let's do an example with this. So what we have is we have a mixture of three different gases. We have hydrogen, helium, and argon, and they're in a container. Now I said the total pressure of the container is 15.6, and I gave you the amounts of each gas. I want to know the partial pressure generated by the helium. So again, pause, take a moment, try to find the answer to this, and then once you think you have an answer, unpause and we'll continue. Okay, so we are looking for the pressure of a gas, so we are looking for the pressure of helium. So that's going to equal the mole fraction of helium times the total pressure. Right, so the mole fraction of helium is the number of moles of helium, which is 2 moles, divided by the sum of the number of moles of all three gases, which is 1 plus 2 plus 3, or in this case 6, times the total pressure, which is 15.6 atm. Right, so this will reduce to 1 over 3, and all we're going to wind up with is 1/3 of 15.6, which gives us 5.20 atmospheres. Right, so all this is saying is that since helium is 1/3 of our gas mixture by moles, it accounts for 1/3 of the total pressure inside the container. Right, so this is a pretty straightforward gas law. Now, for some other gas laws, I'm basically going to, we used to actually teach these three gas laws individually and spend a couple of days on them. I'm basically going to gloss over them and show you the shortcut way of it. I'm also going to give you these equations should you want them. So feel free to write them down if you need them, but we'll go over these kind of conceptually. So we're going to talk about variable relationships, and the variables that I care about here are pressure, volume, and temperature. So we're going to compare two of these gases. If we change one, what happens to another? Right? So let's say that we have a balloon. If we start squeezing the balloon, what happens to the volume? Well, obviously we would expect the volume to decrease because what's happening here? Right? If we're squeezing the balloon, we're increasing the pressure. Right? So increasing the pressure, so pressure going up causes volume to go down. This is what's called an inversely proportional relationship. This is the description of Boyle's law. Now, the equation for Boyle's law is P1 V1 equals P2 V2. Right, so pressure times volume initially equals pressure times volume final. This is how you write the equation for things that are inversely proportional. So that's our first gas law. Now let's take our same balloon, and instead of squeezing it, we're just going to take it and put it in a freezer for a little while. What do you expect would happen to the size of the balloon if we put it in a freezer? Well, if we put it in the freezer, what's going to happen is obviously the temperature of the gas, so T is going to decrease, And what happens is volume's also going to decrease. This is Charles' law. This is a direct proportion. One goes down, the other goes down. One goes up, the other goes up. The way we write the formula for a direct proportion is we actually divide. So we say that V1 over T1 equals V2 over T2. Right? So the ratio of the volumes before is equal to the ratio of volume and temperature afterwards. This is the equation for Charles' law. Our third law is a little bit different. So let's say that we have something that's constant volume. So we have a sealed can. Let's just say soup or something, right? If you put it on the stove while it's still sealed, and then you turn the oven on, what's going to happen? Well, I don't think it takes a genius to figure out that what will happen is the can will eventually burst, right? The reason why is because as we increase the temperature, so temperature goes up, the pressure inside is going to increase as well. Right, so temperature goes up, pressure goes up. So this again is another directly proportional relationship. So the way that we write this is the same way that we write Charles's law. So we're going to say P1 over T1 equals P2 over T2. And this is called Gay-Lussac's law. Yes, he is French, so it is pronounced Guy. And actually that should be T2, not T3. And again, the thing to keep in mind, all temperatures have to be in Kelvin. So these right here are commonly called the three laws. These are the two variable equations. You can use these if you like, write them down, but I'm going to show you an equation coming up right now that will actually make it so you don't need to know these at all. Right, and that equation that I'm going to show you is what's called the combined gas law. The combined gas law is just taking all three of those gas laws, so Charles, Boyle's, and Gay-Lussac's, and combine them into one equation. And we get P1 V1 over T1 equals P2 V2 over T2. So if we change one or more of the variables from a gas, we can figure out what happens to the other variable. Now, the reason why I said you didn't have to know the other three laws is because here's the cool thing about this gas law. If something stays constant, so if it's not mentioned in the problem at all, you just ignore it in this equation, right? So, for example, let's say that temperature remains constant. So we're doing this at constant temperature. T1 and T2 get crossed out. We're left with P1 V1 equals P2 V2, which is Charles' law. Which is Boyle's law. So again, if it remains constant, just ignore it. All you have to do is know this equation and be able to do some algebra. Okay, so let's try a practice problem we'll try a couple of problems with this. I'll show you one that has all three variables and one that just has two variables. So here's our three variable equation. We have 35.4 mils of gas collected at 24 degrees Celsius and 745 millimeters of mercury. I want to know what the volume would be at standard temperature and pressure. Now, it's been a while since I've told you what STP stands for. STP means temperature is equal to 0 degrees Celsius and pressure equals 1 atm. So what this means is you have some converting to do before you can even plug it into the gas laws, right? It doesn't matter what unit you work in for pressure and volume as long as they're the same on both sides. So saying atmospheres and mmHg won't cut it. They both have to be the same unit, but it doesn't matter which one you work in. And again, temperature always has to be in Celsius. So why don't you try this, take a couple minutes, and once you have an answer, pick the video back up. Okay, so what we're going to do is I'm actually going to start off by labeling everything here, right? So 35.4 milliliters of gas is going to be my volume 1. Always label the variables before you begin. It makes your life a lot easier so you know what belongs with what. The two key things people mess up here are not converting and mixing up which variable belongs where in each question. Right, so that's our volume 1. This is going to be our temperature 1, and I'm going to do the conversion here. I'm going to add 273 to this. So adding 273 gives me 297 Kelvin. 745 mmHg is going to be P1. Now, for this particular problem, I think it's easier to convert the atmospheres than it is to convert mmHg, so I'm just going to do that. All right, so what would the volume be at STP? So this is 0 degrees Celsius, or 273 Kelvin, and this is going to be our T2. And P2 is 1 atmosphere, which we said 1 ATM is 760 mmHg. So that conversion was a lot easier to do, which is why I did it this way. Now we plug it into our equation, so I have P1 V1 over T1 equals P2 V2 over T2. Plug in our numbers, so 35.4. Our pressure was 745 over T1, which is 297, equals P2, which is going to be 760, V2, which is what we're trying to solve for, T2, which is 273. Now we're going to do some algebraic manipulation here. Again, if we want to do this manipulation, just remember that all we have to do are those lovely 4 words. Right, so I'm going to say that 297 times 760 times V2 is equal to 745 times 35.4 times 273. Right, so now I'm going to divide. So we did our cross multiply, now we're going to divide this. So 297, 760 on both sides. And we're going to wind up with V2 after we plug this in and we do all of our division. Again, you can multiply the entire numerator, then multiply, then divide if you want, or you can do multiply, 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 divide, divide, and get your answer that way. Either of them is going to give you the same thing, but we are going to wind up with a value of 31.9, and our unit for volume was milliliter, so that's what we're going to keep with here. So 31.9 milliliters. Right, so it's a lot of setup, a lot of work, but again, it's straightforward algebra. Just make sure you do your conversions and that you label everything before you begin, and it shouldn't be that bad. For our second example, this one's going to be a little bit easier because there's only 2 variables that we're going to work with here. You have 38.5 liters at 2 ATM, and we compress it to 9.7 liters. I want to know what the new pressure is. Right, so again, pause, take a moment, and then once you think you have an answer, pick it back up. Okay, so what we're going to do is we're going to label these things. So 38.5 liters is V1, 2 atmospheres is P1, compressed to 9.7 liters, this is V2. We're being asked to solve for P2. There is no temperature anywhere in this equation, so I can say that temperature is constant. That means we can ignore it, right? So we'll write out our gas law, P1 V1 over T1 equals P2 V2 over T2. I can ignore temperatures because it's constant, so we have P1 V1 equals P2 V2. We just plug it in, so 38.5 liters. P1 is 2 atmospheres equals pressure 2, which we're solving for, times V2, which is 9.7. So we're going to get P2 is 38.5 times 2 over 9.7. And that is going to give us an answer of 7.94. Now the unit we are working with for pressure, again, was atmosphere. It's going to be the same on both sides. So ATM. Right, so that is the easy version of the combined gas law, just 2 variables. Again, we just ignore what remains constant and solve it as always.